Okay, welcome back. This is the Virtual Residency Workshop 2023. This is effective communication, how to talk to researchers about their research. So let's dive right in. Okay, so quick outline. We'll talk about research terminology. We'll talk about enterprise IT versus research computing, the mindset gap, types of researchers, what to say to a researcher, how to find researchers, and how to find their projects. Okay, so how to talk to researchers. And this is research terminology. So how many of you believe that oxygen is a metal? By show of hands on your thing, you can do the little raise hand thing. Raise hands. How many of you believe that oxygen is a metal? Galen does. Casey does. And most of you do not. There are only 4 people who say oxygen is a metal. Now, does that make them nuts, or are they right in a certain way? Well, let's find out. So what is oxygen? Well, we kind of all have an intuitive feel for oxygen. Oxygen is that thing that we breathe, and it's what makes it possible for things like fire and rust to happen, right? Oxidation. The chemical term apparently is chalcogen or chalcogen. I don't know what the heck that means. You got to have it to be alive. You got to have it to have fire and water and rust and so on, right? It's an old friend. Everybody knows what oxygen is, right? Now, in one place, oxygen is weird. And that one place is in one discipline. And that one discipline is astronomy. So think about, and by the way, so my PhD advisor is a cosmologist. So he studies the entire universe over its entire lifetime, right? And the universe, the visible matter of the universe, has the following mix of ingredients. Hydrogen, number 1, which is atomic number 1, right? It's just a proton and electron. It represents 75% of all baryonic mass. I don't know what baryonic means in that statement, but I got all this off of Wikipedia, and surely they know better than me. And most stars are actually made of hydrogen that's, burning, fusing, whatever the term is. I'm not a physicist, certainly not an astronomer. The number 2 ingredient to build the universe, at least visible matter, again, we don't really know what dark matter is, but to build the visible matter of the universe, number 2 is helium. And helium is atomic number 2. It's inert, it's a noble gas. It's 24% of the total elemental mass of the visible matter of the universe. I don't know what the difference between baryonic mass and elemental mass is. I don't really care for purposes of this discussion. But everything else combined is 1%. Everything else combined, right? Now, in the world of astronomy, we certainly care about stars and galaxies and clusters of galaxies and superclusters and so on and so on and so on. But we also, down at our solar system level, we care about planets and such. Well, what are planets made of? Planets are made of metals. So, for example, the Earth's core is almost 90% iron, 89% iron, 6% nickel, and 5% everything else, right? The mantle, the outer layer, is not mostly metal, but the core of the planet, most of the mass of the planet, is metals, right? And in fact, it turns out that we paint barns red because there's so much iron that comes to us from dying stars that lands on the surface of the Earth that red paint is cheap, right? That's why barns are red. It's because red paint is cheap. All right, so then what makes a metal a metal? Well, to a chemist, the word metal has a very specific chemical definition, right? And if you look on this diagram here, you can see hydrogen and helium are not metals, right? The orange bits are semi-metals. The green bits are non-metals. Why are red cars more expensive? Because the people who buy them have more money. I'm not going to get into that one. But then, so oxygen is over here in the non-metals, but we have a pretty clear definition of metals in a chemical sense. And then I think we all understand what metals are in the colloquial sense, right? They're hard, shiny things that reflect or whatever. Well, of course, there's the exception that mercury is the only metal that is liquid at room temperature, but almost all metals are hard solids at room temperature and so on and so forth. Okay. But to an astronomer, especially to a cosmologist, the word metals means anything that isn't hydrogen or helium. And the reason it means that is because to an astronomer, what matters are things like stars and galaxies and clusters and superclusters and so on. And planets matter too. And so planets are made of metals. Again, they have other stuff, but to first order metals. So to an astronomer, especially cosmologist, the word metals does not mean hard, shiny things. And it does not mean the yellow bits of this diagram. The word metals means not hydrogen nor helium. And by the way, so I said my advisor is a cosmologist. Well, I had to be in his research group for 3 years, going to weekly meetings discussing cosmology. I was the only computer scientist in the group. I had to go for 3 years before I figured out, and I don't remember how I stumbled on it, but I figured out that when they said metals, they didn't mean hard, shiny things. They meant not hydrogen nor helium. That took me 3 years to figure out. Projection. What's projection? Well, here's a fun experiment, thought experiment. I'm not recommending you do this in real life. You get a mathematician, a psychologist, and a movie producer, and you lock them in a room and tell them to talk about projection. What's going to happen? What does projection mean to a mathematician? Who wants to volunteer? What does projection mean to a mathematician?
Like the
Time
representation
series.
of an object in a lower dimensional space.
Say it again.
Representation of an object in a lower dimensional space.
Yes, representation of an object in a lower dimensional space. So taking something that exists in a higher dimensional space and mapping it to a lower dimensional space. The standard diagram of a cube that's 2 squares with a bunch of diagonal lines, right? That's a projection of a 3D object in 2D, okay? How about to a psychologist? What's projection? Go ahead and shout it out or put it in the chat. No psychologists on? Casey, I could barely hear you. Can you say again?
Oh, I was going to say imposing your subconscious.
On what?
On
someone else.
Yeah, on somebody else. So, for example, ascribing to them a motive for something they did based on that's the motive you would have had, right? Okay, good. How about a movie producer? What does projection mean?
Making light pass through a film.
Yeah, passing light through a translucent medium in order to put an image on a screen, right? So when the 3 of them sit down to talk about projection, how's that going to go? Right? It's not going to go well because they're going to spend their whole time talking past each other. They're going to be using the same word to mean different things. And this is a key problem in effective communication with researchers for research computing facilitators, because they're using words, the same words you use, but to mean different things from what you mean. And they're using different words than you use to mean the same thing, right? So one of the things you have to learn to do as a facilitator is to detect when people are talking past each other, including yourself, and to remediate that, to find a way to get them to figure that out. Now, if you want to see an example of this from classic comedy from the mid-20th century, here's a YouTube link to Abbott and Costello's classic comedy routine, Who's on First? And you'll see a complete misunderstanding between two people, one of whom is using words as regular words, and the other is using the same words as names. Okay, what's a fluid? But what is your doctor or your mom when you're sick? What do they think a fluid is?
Something which flows.
Well, that's okay. So that's on the next slide. That's the physics definition. Give me your mom's definition. What's fluids? You're lying in bed with a cold. What's mom's definition or your doctor's definition?
Liquids.
Water.
Yeah, and in particular, liquids that'll help you get healthy again. What is the colloquial definition of fluids?
Sweat.
That's an example. It's anything that's a liquid, right? But what's the science and engineering, the physical science and engineering definition of a fluid?
Anything not solid.
Anything that's not a solid. So basically liquids and gases, right? So the whole field of computational fluid dynamics, the overwhelming majority of computational fluid dynamics does not study liquids. The overwhelming majority of computational fluid dynamics studies gases, even though the word is fluid. So liquids are incompressible fluids. Gases are compressible fluids, right? And then there are lots of other disciplines that have other definitions of the word fluid, right? What's a database? Give me an example of a database from the perspective of a bioinformatics person. Anybody know? Anybody worked with a bioinformatics person?
Protein sequencing databases.
Yeah, but when they say database, do they mean database like SQL, Oracle, DB2, MongoDB, or do they just mean a big pile of data?
Big pile of data.
They just mean a big pile of data. But if you use the word database to a computer scientist, what do they mean?
Architecture. Software.
They mean something much more specific, right? Much, much more specific. Okay, what is data? And for that matter, what's metadata?
This data is kind of like a measurement represented by a number.
Okay, so is the text of the Iliad by Homer, is that data?
Yes.
To whom?
To someone in literature.
Yeah, someone who
doing
studies
text
classics,
analysis.
for example, or literature, absolutely, right? How about to a chemical engineer? Is the text of the Iliad data to them?
Probably
Unlikely.
not.
Sorry, there are two people talking over each other. Can you try again?
I would say it's data if that's the research question, the information or research question they're trying to answer.
Well, so if they're a chemical engineer, are they trying to answer questions about the text of the Iliad?
It depends on what project they're involved in. But
Well,
I
that's
think what you
true,
wanna
although
say-
I'm skeptical that there are that many chemical engineers studying the text of the Iliad for their research. They might be interested in it as a hobby, but it's the literary folks, the humanists, who are studying the text of the Iliad as they would probably use the term scholarship instead of research, but I think we can settle on the term research for our purposes.
It's
Right, but
digital humanities.
Right.
I mean, data, you think of things as data when you're trying to address a research question.
Yeah, so
whatever's
data
addressing your
becomes
research.
Right. So data becomes essentially a functional definition, right? So now we can't talk about data. We can only talk about what's data to Janet, what's data to Bob, right? Okay. So Casey, I like that NIH definition, recorded factual material commonly accepted in the scientific community as necessary to validate research findings. That's a great answer. Except how useful is that answer to a compiler designer? Right? So we can't agree on what data is. How are we going to agree on anything else? What's metadata, by the way?
Data about the data.
Yes, metadata is data that describes data, right? Is code data? If I write a piece of software, is that data?
To the coder.
So I'm not sure I even believe it's data to the coder, but I surely believe it's data to the compiler designer, right? Or the interpreter designer, the person who converts that high-level language into actions, right? Okay, now let's talk about scale. So let's say we're doing some kind of quantum study, and we're looking at femtoseconds, or for that matter, it could even be down at the atomic level, over femtoseconds. How important is gravity in that context? What is the effective contribution of gravity at the scale of atoms or subatomic particles over femtoseconds? How much does gravity matter in that case?
I guess very little.
Very little. How about to a cosmologist looking at the entire universe over its entire lifetime? How much does gravity matter there?
It's pretty much everything they consider.
I don't know if it's quite everything. They do look at things like chemical species. I benefited from watching them do their work. But it is incredibly important. It's certainly, I would argue it's their number one thing. It's not the only thing, but it's definitely at the top of the heap, right? So the scale at which you operate may impact the extent to which certain factors, I picked gravity, but there are a zillion other issues you could look at. Certain factors play into the research outcomes and therefore the importance that those factors have. If you are in the high energy physics game, you might not care very much about gravity at all. But if you're in the cosmology game, or for that matter, in the mechanical engineering game, you may care deeply about gravity. And there's a zillion other issues. At many scales, in many contexts, most of these factors are effectively zero. They are smaller than the round-off error. But in the situations where they contribute significantly, people care about them deeply. So as I'm going through this talk, I want you to go to this session's Google Doc, and there's already started from last year a bunch of disciplines where gravity does matter and a bunch of disciplines where gravity doesn't matter. And I want you to add to that list and explain as you go. Why does gravity matter in that discipline, or why doesn't it? And if you find a discipline where it's listed, but there's not an explanation for why, and you know the explanation, go ahead and add it in. Okay. Science versus engineering. What does science focus on?
Understanding
Understanding what?
whatever you're studying, whatever
Right.
you want to do.
But an important part of this is understanding reality, right? And what you're trying to do in science is you're trying to discover something important about reality. And often the way that we do this is we poke reality to see what will happen, right? So we apply a treatment to a particular phenomenon to see how the phenomenon changes in response to that treatment, right? So that's discovery. How about engineering? Is engineering focused on discovery about the real world or the real universe?
It's more about solving problems, right?
Yes, and in order to solve problems, you have to design solutions. So science focuses on discovery, engineering focuses on design. And yes, Dean, I agree, you are applying science in order to design something. But engineering is not focused nearly so much on discovery. There are engineers who do discovery, but engineering is focused on design, creating solutions to problems, right? Which raises a question. If you have a design project, is that research? So years ago, I was co-advisor for a master's student in computer engineering. And this master's student was doing some very useful research. I'm getting some fuzz feedback here. Some very useful research on some software. And their approach was they were creating more software. And when we went into the master's thesis defense, and one of their committee members was a much more traditional scientist, the first question the committee member had for us, not for the student, that would have been a bit rude, how the heck is this research? So we had to patiently explain that software research meant designing a prototype and learning about the properties of that prototype. Okay. Do engineers do science research? What about research about software? Is that even research? Right? CS versus IT. What is the difference between computer science and information technology? Let me ask that question a little differently. What is the difference between computer science and information technology to a computer science researcher?
How versus what?
So there's some truth to that, but I want to get even more stark. So in my experience, the difference to a computer scientist between computer science and IT is plumbing. It is morally equivalent to plumbing, and IT professionals to a computer scientist are morally equivalent to plumbers. Okay. It is not considered a serious thing, even though it is the enabling technology for all the other stuff, right? So what happens if you refer to a computer science major or computer science researcher as IT? How do they respond? And by the way, I've actually seen this happen in practice.
Before we move on, in that analogy, what is computer science? The water?
I'm sorry?
Electricity? In that analogy, you just put out, computer science is what? Water?
No, computer scientists are researchers and IT people are plumbers.
Gotcha.
Yeah. So yes, Renata, very good. Yes, they get very defensive and angry and insulted. Yes, and I watched this happen because I was on a project that had computer scientists and ecologists, and one of the ecologists referred to what the computer scientists were doing as IT, and you could almost hear that record scratch sound, right? And everything stopped dead. And then one of the computer scientists politely corrected the ecologist. No, they really don't take to that at all. Now, by the way, do computer scientists do research? Okay, Renata has the correct answer, right? So computer scientists do research, but a lot of domain researchers think of computer scientists as they're just here to help us do our real research. And that doesn't go over well either. In fact, a lot of computer scientists don't like to collaborate with non-computer scientists for exactly that reason. They don't want their research to be treated as just tool building for the real researchers. They're not interested in that. Okay, is simulated data data? So many of us have helped researchers run simulations, right? A simulation produces output. Is that output data? Okay, you're all saying yes. I'm going to tell you what the chemical engineer told me. Not just that the answer is no, but that if he referred to the output of the simulation he wrote as data instead of as simulated data, he would be laughed out of the conference. So you have to be super careful. Not everybody agrees that everything we think of as data is data, right? What are some of the disciplines where what we think of as data is not data, and what they think of as data is not what we would have thought, right? And of course, as I mentioned before, a compiler designer thinks of code as data, right? A piece of code is input to a compiler. Now, here's a tough one. Everybody's guilty of this, starting with me, right? You're explaining something, you assume that they know what you know while you're explaining, right? Maybe not the exact thing you're explaining, but they know everything else you know. That is the most normal thing in the world, to assume that the person you're talking to knows what you know. The second most normal thing in the world is to be dead wrong about that. They don't know what you know. And everything that you think they know, they don't know. I'll tell a story. The guy who taught me how to write grant proposals, we were working on this particular project, and he described a thing he wanted a piece of code for that I was volunteering to write the code for as part of this project. He described the thing, and I said, oh, that's a binary tree. He said, it's a what? I said, it's a binary tree. It's like freshman computer science. He said, I've never heard of that. And I was flabbergasted. By the way, this was 20 some years ago. I was utterly floored by this. How could anyone possibly not know what a binary tree is? How is that even possible? And then I thought to myself, well, where would he have heard about this? Right? Because he was a chemical engineer. All his training was in chemical engineering. When the heck would binary tree? It came up in freshman year for me. But why would it ever have come up for him? And the short answer is it never would have. Right? Of course he didn't know what a binary tree was. So what was obvious to me was completely opaque and unknown, terra incognita to him. And we're really bad. Human beings are incredibly bad at this whole talking to each other and working things out on the basis of the same of shared understanding, right? So I stumbled on this just this year, just a few months ago. A study in Scientific American, the probability that two people selected at random will share the same concept about penguins. What is a penguin? Is 12%, 1 in 8. 1 in 8. If you pick two people at random and say, talk about penguins, 1 in 8, they'll be able to share the same, roughly the same notion of what a penguin even is. Now that seems astonishing to us, right? All the slides are available on the webpage, Stacy. That seems astonishing to us, but it's actually really how people are. And when you're talking to people, when you're helping people, when you're explaining to people, working with people, you have to bear in mind that all these things that you think you share with them, all this knowledge that you think you share with them, you are dead wrong. You don't share that knowledge with them. They don't know that. Whatever it is, they don't know. We can't even agree what a penguin is. There's a 7 in 8 chance that you will run into someone who disagrees with that. Every person you run into, 7 out of 8 of them will disagree with you about what a penguin is. What a penguin is. Okay. Researchers found that only 2% of conversations ended at the time both parties desired. They were doing a study about how to end a conversation or how people end conversations. And they found that 98% of conversations go on too long or end too early. Mostly go on too long. People don't know when to shut up, right? Only 30% of the conversations ended when one of them wanted it to end, let alone two, let alone both, right? Thank you, by the way, to Bev Corwin for these references. It's fantastic. Okay, so go to the web page, right? Go to the Google Doc. The link is on the workshop webpage. Go to the Google Doc and enter a piece of terminology, a term that's used in many disciplines and subdisciplines and sub-subdisciplines. Write down the term and what discipline and what it means in that discipline. Go ahead and do that. And you can do that as I continue. I'm not going to sit around wasting time waiting, but go ahead and add that in. Okay, we're only on slide 20 of like 80, so I'm going to keep going. But go ahead, go to the web page. The link is on the website. Go to the web page, click, add some stuff in. We want to make this list huge because ultimately we want this list as a shared vocabulary lesson that everyone can go to and refer to and say, okay, I didn't realize that this term meant this thing in this discipline. It's never going to be big enough, but it'll be big enough to give us the idea that at minimum, we've got to ask the question, is this the thing you mean? Because a lot of the times when we're working with researchers, it doesn't occur to us to say, okay, when you say mesh, do you mean a grid lattice or do you mean like a net that you would catch fish with? Right? It never occurs to us to ask that question, but that question is crucial to understanding what they're talking about. I spent, I think it was 2 years, talking to this one grad student about their simulation of an oil reservoir without understanding what an oil reservoir is. I thought they meant a big puddle of oil. And boy, was I wrong. What they meant was a rock, a giant rock with itty bitty tiny pores in it. And the itty bitty tiny pores inside this giant rock had oil inside them. This is the exact total different thing from what they meant. And it took me 2 years to figure that out. I'm an idiot, by the way. But I don't think I'm an unusually dumb idiot. I think we're all this dumb, right? So ask. Okay, now I want to turn to sort of the next section and talk about enterprise IT versus research computing. Are they natural enemies or are they natural allies? And I hope I can convince you that enterprise IT and research computing are natural allies. That's certainly been my experience. But to make them natural allies, you, coming from the research computing side, have to take the extra step. And the reason you have to do it is because we in the research computing business are by far the minority. Enterprise IT is the vast supermajority. Okay. So in enterprise IT, what do they care about? Well, everything has to be secure. It has to be established technology. They have to use best practices. Because what they're trying to accomplish is 5 nines. They want 99.999% uptime, which translates to 5.25 minutes of downtime per year. Right? That's a lot of uptime. Why do they need that uptime? We'll look at that in a minute. Research computing is the exact upside down of enterprise IT. We want, I'm not making this up, 1.5 nines, 95% uptime, right? We need to be fast and flexible, got to be able to turn on a dime, right? Today we're doing such and so. Tomorrow we may get an email from a researcher with a giant pile of money, so the university cares very much, who says, I need to do this totally new thing that you guys have never done before. Okay, now we're doing that new thing. The university needs it. It's important. Now suddenly it's a priority. We never thought about it before, and suddenly we're going to do it. It's got to be cutting edge technology. And by the way, in the world of technology, you have exactly 2 choices. You can have established technology, which means obsolete, or you can have new technology, which means broken. So in research computing, we're in the broken technology business. And in fact, at my institution, we expect them to deliver us broken technology. What we want is they then help us fix it, right? Sometimes by sheer dumb luck, they'll deliver us working technology, but sometimes they deliver us broken technology, and that's fine as long as we can work together to get it into production, right? That's fine, right? And there's often no such thing as best practices, right? And security standards are different for research computing. In fact, there was just a publication that came out from the federal government talking about, for the first time, by the way, security standards for research computing. This is a brand new thing, right? Security for enterprise has been going on for 50 years or more. Security for research computing, it's not literally brand new, but this is the first time that someone's tried to produce more or less a standard for research computing, more or less. And interestingly, in that document, the overwhelming majority of the document is just describing research computing systems, right? They got to get deep into the document before they even start talking about security. First, they have to explain what the research computing systems look like. Okay, so what you end up with is 1.5 nines, 95% uptime. That's 18.25 days, 438 hours of downtime per year, right? So a day and a half, 36 hours of downtime per month, right? Compared to 5.25 minutes of downtime per year, right? And I'm not making this up. You can go look at NSF solicitation 23-518 today. This is an active solicitation, right? Or maybe it just closed, I can't remember. And it says, NSF-funded production resources should be unavailable as a result of scheduled and unscheduled maintenance no more than 5% of the time. Now, here at my institution, research computing, we actually run at 98.8% uptime, and enterprise is actually running at 99.995, so about 4.5 nines, and we're at not quite 2 nines. Right? But same principle. Now, why on earth would the enterprise IT folks need 5 nines? And why on earth would the research computing folks tolerate 1.5 nines? Well, the answer to both questions is the exact same answer: money. Here's an example from enterprise IT. This is now, 7 years ago? Delta had an outage in their Atlanta data center. They were down for 5 hours. It cost them, they reported that it cost them $150 million. That's $1 million for every 2 minutes of downtime. When you got $1 million for every 2 minutes of downtime, your job as enterprise IT is to make sure there's no downtime. And if there is downtime, heads will roll, or at least assistant heads. Okay. Now, on the research computing side, as I said, things are different. So on the enterprise side, let's say tomorrow is payday, and tonight the payroll system goes down. Well, tomorrow, everybody's furious because they didn't get paid, right? Of course they're mad. And heads roll, or assistant heads, okay? So if you don't want to be selling pencils on the street out of a tin cup, if you want to stay in the enterprise IT business, you got to make sure that that machine is never, ever down. Because it's not going to go down when it's convenient. It's not going to go down right after everybody gets their paychecks. It's going to go down right before everybody gets their paychecks. We know Murphy's Law, right? So to stay in business, you've got to do the 5 nines, right? But on the research computing side, if you're not cutting edge, you're not going to get fired today for not being cutting edge, but eventually over time, you'll be less and less useful to your researchers, and therefore less and less valuable to the institution until eventually you're so not valuable that they get rid of you, right? So to stay in business, you've got to stay on the cutting edge, okay? But on the other hand, in research computing, you can afford to be wrong. You can afford to make mistakes. And let me be real specific about what I mean by that, okay? So let's say you've got a system that crashes occasionally. Heck, let's say you've got a system that does 438 hours of downtime per year, right? That's the NSF standard, 95% uptime, okay? Well, what is the implication of that? 1 24-hour day on an HPC cluster, on a supercomputer, what does that translate to? At a typical institution, on any given day, you're going to have 10 to 100 users, mostly grad students, right? Mostly grad students running on that machine, 10 to 100, okay? So if you're down for 24 hours, you've lost 10 to 100 grad student days. Well, what's a grad student make? About 30K on the high end, right? Fully loaded with tuition assistance and fringe is usually kind of small, and overhead, indirect costs, facilities administration, whatever you like to call it. It's about 60K. So 100 grad student days, that's about $16,000 of lost productivity. By the way, even that's an exaggeration because it's not like grad students, the only thing they do is sit around waiting for their jobs to run, right? They're writing papers, they're taking courses, et cetera, et cetera. But in the worst case, 16K of lost productivity. And typically those 10 to 100 grad students are from 5 to 50 different research teams. So per research team, you're losing from 3 figures to low to mid 4 figures per research group for a full 24-hour day of downtime. Well, what do you get for that? Well, here's the thing. The number of 9s, that's not a knob you can turn, right? That's a stair step. You're either at 1.5 9s or you're at 5 9s. And the problem is 5 9s. I used to think that cost double. And I was explaining that to a person from one of the big IT vendors, and they laughed at me. They cruelly mocked me, and they said, it's not a factor of 2, it's a factor of 10. And they didn't say idiot, but it kind of hung in the air, you know? So if the cost of going to 5 9s means the cost of the same amount of research computing goes up by a factor of 10, does that mean that the budget goes up by a factor of 10? Of course not. The budget doesn't go up at all. So what happens is if we implement 5 9s, what we get in exchange is 90% productivity loss, right? We can only provide 1/10 as much research computing capacity as we could with 1.5 9s. So we make the trade-off. We'll give up a ton of this stuff in exchange for, we'll give up lots of uptime in exchange for vastly higher aggregate research productivity per year, because faculty don't get evaluated by the hour, they get evaluated once a year. So how much failure is normal? So here's, sorry, that should say calendar 22. I just ran these numbers last night. So in calendar 2022, we ran a little under 5 million jobs, of which a little under 500,000 failed, right? So about 8% of all jobs failed. Of the jobs that failed, only 14,000 failed because the server failed. So that's 3% of the failed jobs and 0.25% of all jobs. And by the way, even that, I was using node fail as my way to decide that the server had failed. Even that's an over-exaggeration. A lot of cases, what happened was the users were consuming too much RAM, and so the node crashed, or something along those lines. Node crash as opposed to physical failure. So hardware failures are almost unheard of, not literally, but almost unheard of, whereas job failures are commonplace, right? 8%, 1 in 12 jobs fails, right? Fails, not canceled, not ran out of time, genuinely failed, 1 out of 12, right? Failure of the job is normal. Failure of the hardware is not. Right, yeah, most of node fail is because you ran the node out of memory, right? Okay. So what are the implications for IT? Well, research computing is cheaper than enterprise IT because it's 1.5 9s instead of 5 9s. And I mean that per unit of capacity, but it's also way less resilient. So when a researcher comes to us and says, I need a specific thing for a specific project, the question we should ask is, can you tolerate about 8 hours of downtime per month? Because again, we're running closer to 99%. If it was 95%, then it'd be whatever, 30 hours of downtime per month, but we're running it more like 99%. So can you tolerate an average of about 8 hours a month downtime? And if they say yes, we're going to be able to do it way cheaper than the enterprise side. But if they say no, then we send them to the enterprise side because that's what they're going to need. Right. And we actually had a case a few years ago. This was right before Christmas. I met with a group where they had some stuff that was perfectly happy on 1.5 9s and some stuff that needed 5 9s. And so the answer was easy. Okay, the stuff that's happy with 1.5 9s, come to us. The stuff that needs 5 9s, go to them. And by the way, we and them, we're all sister teams within OUIT. So it's still all us, but there's research computing versus the enterprise side. Okay, and we're also a test bed for enterprise. By the way, I'm going to run out of time way before I run out of slides, just so you know. So research computing has limited best practices, but we're constantly adopting new technologies. And so, you know, and we don't know what we're doing when we get these new technologies. It's the standard joke, right? So if we knew what we were doing, it wouldn't be research. So we try a new technology and then we make a bunch of mistakes. Enterprise can watch us make those mistakes, learn from our mistakes what not to do, what the best practices should and shouldn't be. And then they can adopt those same technologies after we do, right? And a beautiful example of this, we moved into our current data center in 2012. We were the first group in there. We told our users it would take 1 to 2 weeks to move the supercomputer from the old data center, which had constant power and cooling failures, to the new data center, which was shiny and sparkly. We said it'd be 1 to 2 weeks, and it was 1 week and 1 minute. At 5:01 p.m., I sent the email to all the users saying you can get back on the machine. That was on Friday, 5:01 p.m. But so we were down for a week, and then we found out space, power, cooling, network, everything was working beautifully. And so after that, the enterprise folks were able to start moving in. We had the luxury because if we were down for a week, it wasn't the end of the world. If they were down for a week, that would have been the end of the world. Okay, the mindset gap. So switching gears again. I mentioned about the laptop versus handheld thing. In the olden days, it was the laptop world. And in the laptop world, we were still pretty far from Linux, command line, remote shared batch, right? But now that it's handheld, right, that's way worse. Okay, it's way, way farther. So how does that change our job? Well, if you're going to, let's say, install software on your phone, what does that take? Well, you do 3 taps, right? 1 tap to open the store, the app store, 1 tap to pick the app, and 1 tap to give it permission to listen in on all your phone calls, right? If you're going to do that on a supercomputer, what's it going to take to install a user application? Well, if you're lucky, you can do it with Easy Build or SPAC, right? Which are tools for building software. If not, maybe you have to do that configure, make, install thing. And hopefully there aren't a lot of dependencies where you have to install something else first. And in real life, a lot of the times it's just some bizarre weirdness because the people who design the software are not software designers. They are scientists or engineers in that particular research domain. And they've done the best they could because they had no training in how to design software, let alone how to design the build package for the software, right? It's not realistic to expect our researchers, some of our researchers can learn to do that, but not all of them, right? How about storage? What do you got to do on a phone to install more storage? Well, if the phone has the little slot in the side, then you can go to your local big box store or wherever, and you can buy a little micro SD card that has greater capacity, and you're probably going to pay between 10 and $100 for that. And then you pop that in the slot, and the thing within seconds recognizes it and is ready to use it, and you are good to go. You've got your storage. So it cost you a few dollars, and you popped it right in, you're good to go. Right? How about large scale? Well, first you have to design what you want, then you write an RFP, then you hold the RFP, then you evaluate the bid responses, then you make a selection. At my institution, if that's going to cost $1 million or more, it has to get approved by our regents, right? Our governing board. Then you make a configuration, what you actually want based on the pricing you got. Then you purchase it, you deploy it, you maintain it, you maybe expand it, you ultimately decommission it. Just getting it on the floor is going to take at least several months, maybe a year or more, right? Let alone the lifetime of the thing, right? Because it's going to be in production for, you hope, several years, right? It's a completely different procedure. Imagine you go to the grocery store And you get to the grocery store and you say, I want a bag of oranges. And they say, that's fine. First, you need to talk to the warehouse and you need to work with them on finding an orange vendor where they can get oranges by the truckload, and then they will get a bag of oranges in the next truckload of oranges for you. That's not why you go to the grocery store. You go to the grocery store to get the bag of oranges, right? All right, but then there's this issue of cost, right? As I said, with storage, handheld, you're talking about tens to at most hundreds of dollars. Laptop, pretty much the same, maybe thousands if you're going real big, right? At large scale, a petabyte for a single copy, a petabyte of tape is going to cost you $5,000. A petabyte of spinning disk is going to cost you on the order of 10 times that, and a petabyte of SSD is going to cost you 60 times that, right? And at the scale we're talking about, petabytes are normal. Right? So the issues, and we mentioned this before, the issues that are driving this, research computing is hard because of the mindset gap, which we already talked about. It's hard because research computing systems are always getting harder to use. The storage hierarchies get deeper and deeper all the time, right? Optane now is being replaced by, what is it, CXL or whatever it is, which is a standardized thing, not limited to one vendor. And now, of course, there's high bandwidth memory, is just becoming available through the new Sapphire Rapids CPUs. And then parallelism is getting more and more hybrid, right? MPI on top of GPUs, or maybe MPI on top of OpenMP on top of GPUs, and so on and so on and so on, right? And then more and more researchers, more disciplines, and a higher fraction of researchers per discipline need research computing. Why are researchers the way they are? And Bruce Mason has a session about this after lunch, so you don't want to miss this. I'm just going to skim the surface of this. Bruce is going to take us right into the heart of the matter. It's an amazing session, and you will be so happy that you had an opportunity to hear from him about it. Okay, so we got faculty, we got staff, we got students at an academic institution. If you're at a government lab, faculty and staff are really more or less the same kind of thing. Same thing typically at a nonprofit research institute. I'll be perfectly honest and say in the commercial space, I don't really know. Okay. At academic institutions, which is I think where most of us are from, what are faculty rewarded for? They're really rewarded for three things. And by the way, depending on the nature of the institution, the order in which these matter adjusts. But bringing in grant money, publishing papers, graduating students. Certainly at a research-intensive institution, it's those three things. Now, I'm not claiming an order. Well, I kind of am, but let's pretend I'm not. At a teaching-intensive institution, much more emphasis on graduating students and doing research, less emphasis on the grant money and the publishing. I'm not going to say no emphasis. There's certainly a lot of reward for that, but less expectation. Okay. What faculty aren't rewarded for is having good IT. Right? Spending a lot of money on computing systems and services. There is no reward for that. In fact, they're implicitly punished for that in the following sense, that if they had spent that money, instead of spending that money on good IT, they had spent it on more grad students, more researchers, then they would have more research productivity, so they would get more reward for that. Right? Now, we can make the argument, oh, well, this will make all your researchers more productive. But when you don't have enough researchers to begin with, that's not as compelling an argument. Right? So they'd like to spend zero. If they can't spend zero, they'd like to spend the absolute minimum for IT, for computing, right? And their mental model for what it should cost is USB drives from Walmart, right? If they can't get it for that price, they feel like they're being ripped off because that's their expectation. And remember, satisfaction equals reality divided by expectations, or if you like, reality minus expectations, right? If you can't improve reality, lower expectations. Okay, so let's talk about tenure track faculty, people who aren't yet tenured. Okay, what's their incentive structure? I got to publish lots of papers, I got to graduate a lot of students, I got to bring in a lot of grant money, or I'm fired, right? So I need things to work right now, and I need them never to stop because I have a very short timeline to doing all the work that I'm going to be judged on for deciding whether I get tenure or not, right? I've got typical for a new tenure track faculty is 7 years, but that 7th year is really the transition year. If they didn't get tenure, that's the year that they have cushion time to find a new job. So it's really 6 years, except that 6th year is when they're being judged on whether they get tenure. And that process takes quite a while, right? They have to put together a big package that's got to be sent out to external reviewers, plus the executive committee within their department. And then it's ultimately going to go to the whole faculty in their department, and then to the dean, and then to the provost, and then to the faculty senate or somewhere. And I mean, all these different, and then ultimately the president and the governing board, regents, or whatever you call your governing board. And on and on. I mean, there's a whole bunch of layers, right? And each one takes time. So I really have 5 years, except in most disciplines, you get judged on journal articles and or publishing a book. Journal articles typically take 6 months from submission to appearing, or even acceptance, right? Because they have to go through multiple layers of review, and it's a whole big thing, right? And you might have to make changes to it, and so on and so forth, right? A book, I don't even know how long it takes to get a book published. So probably I've got something like 4.5 years to do everything that I'm going to be judged on whether I get tenure or not. That's a pretty heavy lift. I've got 0 tolerance for downtime. Now, if I've got tenure, right, it sounds like I'd be more calm then, but the reality is I had 7 years of building those mental habits. So it's too late for me, right? Okay, so chemistry, they're now down to 2 to 3 months. Okay, so that buys 3 to 4 months on that 4.5 year timeline. That's good. I don't think it's a game changer. But they still have the same incentive structure. Graduate students, publish papers, bring in grant money, right? Because if they don't do that, they don't get a merit raise. They don't get that named chair they've been itching for, which comes with a salary bump. It comes with additional funds like for hiring students or whatever. I won't get elected into my national academy or whatever it might be, whatever the prestige things are that are rewards, which then of course also translate into things like merit raises and so on. So again, everything has to work now, and it has to keep working reliably all the time. Now, what if I'm research faculty? So I'm not on tenure track. Well, if I don't bring in grant money, I can't pay my own salary, right? My salary is soft money. So if I can't bring in the money, I'm out, right? I got to publish a lot to bring in the money, right? And I got to establish a track record of graduating students so that I can get a tenure track job, because I don't want to live on soft money forever. I want to get a proper hard money job. And that in practice may very well mean I want a tenure track faculty position. Right? Postdocs. I got to publish, otherwise I'm out as a postdoc, right? I got to learn how to get grant money because I want a permanent position. Right? And students, well, the number one goal of a student is to graduate, right? That's their job, is to graduate. And anything that delays graduation costs money. Maybe they're on a scholarship or grants or loans, whatever it is, but every additional semester is extra money. And the longer I stay in school, the more it's costing, not only in the money I'm paying out, but in the foregone salary and benefits that I would be making if I had already graduated, right? I ran the numbers some years ago to figure out, and this was in then dollars, not now dollars. But I calculated, based on how long I was in grad school, I calculated that my PhD cost me between $250,000 and $500,000 in foregone salary and benefits, not including interest, just the actual raw dollars paid out to me, somewhere between $250,000 and $500,000. Okay, now let's talk about research funding. Okay, what's the academic research funding model? I would characterize it very simply. A random amount of money shows up on a random date and is available for a random duration, right? Typical is 2 to 5 years. There are some that are shorter. There are some that are longer, but typical. In fact, 3 years is probably the most typical, right? And depending on the institution that you're at, it's very common at our ones that are not sort of top 25. It's very common. The most common is a 6-figure grant. There's some 5-figure, but they're not that common. They're not that usual. And then there are 7- and 8-figure grants and maybe even 9-figure grants, but those are very rare, right? Especially the 8- and 9-figure grants. Very, very rare. Anybody who brings in one of those, they're an automatic hero and they get whatever they want, right? Because there just aren't that many of them, right? At my institution. Now, if you're at a top 25 institution, they may be commonplace. Maybe an 8-figure grant is like normal and everybody has an 8-figure. I don't know. But okay. But random amount of money shows up on a random date, available for a random duration. Everything that you do in research computing has to be built around that model, has to assume that model. There's no nice, steady income. If you report up the chain of command to the CIO, whether directly or through others, you're accustomed to IT has a budget every year. It may go up and down depending on the vagaries of the overall budget of the institution, but it's relatively steady. With researchers, that's totally not the case. They may be completely flush this year and absolutely dead broke next year. And I've seen it happen where someone had 8 figures and then they had nothing and then they had 8 figures again. It's normal, right? Grants like to pay for researcher salary and fringe. They hate paying for really anything else. They will pay for some of those things some of the time, but they really don't want to. They'd really rather spend the money on researchers, right? So it's hard to get money for equipment. It's hard to get money for services. It's very hard to get money for non-research staff, okay? And there's not much credit for any of that, right? If there are recurring charges, because remember, it's a random amount of money, shows up on a random date, available for a random duration, recurring charges are really hard. So let's say I have a petabyte of data and I stick it in a commercial cloud, right? And I've got a 3-year grant. Great. 36 months, that data sits in the commercial cloud. Month 37, the cloud provider will be happy to delete that data for me. And I can't really put it on my next grant unless my next grant is specifically about that data. Because if my next grant is about some new thing, which it probably is because the research funding agencies favor innovation, if my next grant is about a new thing, I can't justify paying for that, for the monthly recurring charges for that petabyte on my next grant. So I'm screwed, right? Now, at some institutions, some of the academic research is internally funded, for example, by the endowment, right? Especially at high-end institutions. The problem with the top 25 is there's only 25 of them. Same thing with the top 50 or the top 100, right? Most institutions have very limited internal funds to support research. Some institutions have none at all. Very few institutions have a lot. Now, getting external funding is a law of large numbers thing. You got to submit a lot of proposals to get a few proposals funded, right? So if the NSF, sorry, that should say fiscal year 2022. I don't know why I didn't update that. For fiscal year 2022, 28% of proposals were funded. That's actually up a bit. I think the previous year was 26, right? And you can see it varies by directorate. And computer science does pretty well. And cyber infrastructure is actually number 3 in terms of success rate. So we're actually doing pretty well. But it's still, you got to submit, on average, for cyber infrastructure, you have to submit 3 proposals to get 1 funded, right? Which means, by the way, your faculty spend a lot of time writing grant proposals if you're at a research-intensive institution. And then I broke it down by state and territory, by jurisdiction, and I broke that out by EPS score and non-EPS score, just to give you a feel for this. Okay. So, what do they put into research computing? What are the funding models? Well, there could be some internal funds, and that's typically on a regular cadence, like it's in the annual budget, perhaps from the endowment. You could get internal funds at a random time. This has certainly happened at my institution. Hey, let's buy a supercomputer. That was our first supercomputer. was, hey, let's buy a supercomputer, right? And somebody came up with a pile of money and we bought a supercomputer. In other cases, it could be that there's, you do a lease or something, and then so you're paying for it on a regular cadence, even though you bought it in a lump sum. You could get grant funds, those show up at random times, and you buy a supercomputer with that. So if you get a major research instrumentation grant, or you get a campus cyber infrastructure compute grant, or there are other programs as well, but those are the two that come immediately to mind, right? At public institutions, you might have a state appropriation. I will tell you that at my institution, we have carefully not pursued that on the theory that the state giveth and the state taketh away. And we've seen happen in some other states where they have a state research computing budget line item, and then there's a bad budget year and it's gone. And we don't want to be subject to those kinds of outcomes. And so we've avoided that. You can do usage charges. There are not that many institutions that charge by the core hour, in large part because when you do that, the faculty either don't do heavy computational research or take it to the national centers, in which case they're much curtailed because the national centers have nowhere near the capacity that's actually needed. Or you can have faculty buy chunks of your supercomputer, what's called condominium purchases, and that'll happen at random times, right? Okay. At my institution, we don't ask faculty to write proposals for time on our machines. And there's a very specific reason why we don't do that. I mentioned before, they spend a lot of their time writing proposals anyway, because to get external funding, it's a law of numbers. You've got to write lots of proposals to get a few of them funded. And so we encourage them to spend their proposal writing time getting external funds, not getting permission to use an internally funded machine that's already been purchased, right? We want them to go bring us more money. They bring the university more money. The best way to do that is not to make them spend time doing stuff that isn't that. Okay. I'm very low on time, so this is probably as far as I'm going to get, this little section here. So things you can say to a researcher. This other way of doing the same thing you want to do is cheaper than how you're doing it right now or how you want to do it, right? Or for this same cost of what you're paying, here's how it could be so much better, right? They love hearing that. You get to decide how you use your own piece. You get to decide who uses it, right? They love that. Your students are not going to have to spend time being system administrators. Right? They can be productive in their research instead of being distracted by making the machines run. All of those things are things researchers love to hear. And how do you find researchers? So here's how I do it. I go to the website, right? ou.edu, yourinstitution.edu, whatever it might be. And I click on academics, and then I drill down to the individual departments, and I look at the faculty list. And I just read their research descriptions. And I look for keywords. And there are a bunch of them, and they vary by discipline, right? But computational, numerical, in engineering in particular, they use the word numerical to mean computational, right? Parallel, that word usually shows up in computer science. Informatics, that shows up in a lot of different disciplines, obviously biosciences, but other places as well. And then chemistry, you look for computational chemists. That's becoming a thing. That didn't used to be very common. For a long time, the computational chemists were masquerading under the term physical chemists. And the reason they did that, I suspect, is because computational chemistry was somewhat poo-pooed by their non-physical chemistry colleagues, their colleagues in other areas of chemistry. Well, that's less so today. So we're starting to see more faculty listing their area of chemistry as computational chemistry. But for a long time, that wasn't true. And by the way, they have the word calculation. So you look for calc instead of compute or numeric, right? They use the word calculation a lot, the chemists, right? There's sort of a general set of vocabulary words that you get accustomed to looking at as you do this exercise, right? Then when you find people who have those kinds of keywords in their research description, send them a cold email. Tell them what you do, tell them what your organization does. If you're writing a proposal, tell them what program you're submitting to, when it's due, and how much they're going to get. And I don't mean they're going to get a piece of cash. You know, they're going to have access to this wonderful machine or whatever it is you're doing. And ask them what their needs are with respect to research, computing, and data. Right? Go to the meet and greets, right? Faculty, there's new faculty events, there's things like that. Now, I like to, from time to time, check in with the minutes of our Board of Regents meetings, our governing board, because they include all the new faculty. And I'll just look and see, are there faculty in likely departments who are new? And then I can go look up their research description and say, oh, well, it appears that Lee, our new faculty member in chemical engineering, is doing some computational stuff. So I'll just send a cold email to Lee and kind of get the ball rolling, and maybe something will come out of it, maybe it won't, but writing that email took me 5 minutes, right? Totally worth the trouble. Okay, go visit them. Now, I know we're in the post-COVID era, so some people would rather visit by Zoom than in person. That's fine, no big deal. If you can visit them in person, that's great. So have you ever noticed that vendor reps love to come visit, and they are constantly asking, hey, can I come visit? Hey, can I come visit? And even better than visiting, hey, can I take you to breakfast? Can I take you to lunch? Can I take you to dinner? And even if you have to refuse to let them pay, they still want to go. Oh, well, let's go, and we can each pay for ourselves, right? No big deal. Why? Because there's something magical about A, in person, and B, breaking bread with someone. It's literally magic. There's some weird psychological magic that happens when you meet with someone in person. You like them more. By the way, on average, you like them more, you trust them more. And when they're visiting you, unlike on a Zoom meeting, let alone an email, on a Zoom meeting, if you run out of the original subject to talk about, you'll just end the Zoom meeting because everybody wants to go off and do something else, right? But when you're meeting in person, if you've booked an hour, you'll stay for the full hour. Even if you run out of stuff to talk about, you'll talk about other stuff. And you'll get an opportunity to talk with that person about things that they weren't planning to talk about. And you'll hear about stuff that was not part of the agenda of this meeting. And if you're sharing food, I don't mean literally like you're sharing it from the same plate, but if you're having a meal together, the psychological magic is even bigger, right? And then ask them questions like, what's your research about? What are the computing parts of it or the data parts of it? And of course, that one about if you had an infinitely large, infinitely fast computer, what research would you want to do, right? So here's an exercise that I talked about before. If you haven't done it already, let's go ahead and do it now because we're coming to the end of the talk. Go to that web page and add in more vocabulary or more definitions of the vocabulary marked by discipline or subdiscipline or sub-subdiscipline. Let's build a community resource of vocabulary to help people who are working with researchers in a discipline that they're not familiar with. And that's it. And I have -1 minutes for questions, but I'm willing to spill over a little bit. And I will give 5 brownie points to the first person who asks a question.
After this slide, there are more slides, including how to find research projects and interviews.
Yes,
how did
there
you plan
are.
on utilizing that? And how can we invest our personal time to make sure that we cover that topic?
So I don't think we're going to end up having any open time. I've asked all the speakers and moderators and panelists to not have dead air, meaning keep talking until the clock runs out. So I don't think we're going to have any extra time for that. However, I think in past years, I might have gotten to those slides. So you might want to look at previous years' videos and see whether I got that far, and you can see me discussing those. Or I am very careful to fill my slides with complete sentences, so you can actually read the content, and that'll get you at least a good feel for some of that stuff.
Henry, it's David Reddy from South Carolina, and you commented that you don't make researchers write proposals or effectively grants for computing time. do you make them write data management plans to get storage?
No, that's taken care of in their proposals. So we don't impose that on them in their in getting the stuff. The real question is, to what extent are data management plans enforceable? And I would argue that at the institution level, that's very, very difficult. Because data management plans can be highly idiosyncratic. To the extent that they are enforceable, they will have to be enforced by the funding agencies. And the pattern does seem to be going in that direction. I think where we'll really start to see data management plans being used as a mechanism or an enforcement mechanism for data management plans will be when the funding agencies require PIs to list as part of their results from prior support, or whatever it's called for the various funding agencies, to list how the data products were managed.
Well, I want to clarify, though, talking about data management plans, like basically the on-site, storage and eventual archiving, even if the archiving is offsite, versus the data sharing plan, which is what the funding agencies really care about.
Well, so the funding agencies are now requiring, NIH is now requiring both data management and data sharing. I expect all the other federal research funding agencies to follow suit at some point. NSF, I think, probably pretty soon. So Jeremy, I agree, but I think, so Jeremy says funding agencies won't track data management until there's a reasonable way to do it efficiently. I think the way that they're ultimately going to do it is to make the next chunk of funding contingent on reviewer satisfaction about the previous chunk of funding. And that's the results from prior support. That looks to me like a mechanism. Why should we woo researchers? Aren't they supposed to come to us? I would love to live on that planet. But my experience has been, A, they don't know we're there. B, if they do know we're there, they think they can do it without us. And C, they don't understand how valuable we can be to them until they're in the throes of things. And we want to get the jump on it and get them on board. And let's be honest, get them hooked, get them to rely on us so that they'll continue to be consumers of the capabilities that we provide. So I'd love to believe that if you build it, they will come. But my experience has been, no matter how good the thing is that I produce, if I don't chase after them and needle and wheedle and beg and plead, they don't show up. And by the way, the proof of that is this very event. How many of you received at least 3 emails from me about this event prior to the event, begging and pleading for you to sign up for this event? 3, try 30, says Horst. Yeah. Okay. So you see my point, right? If that doesn't work on us, why would we expect it to work on them? So we beg and plead and wheedle and needle until we get them signed up, because that's what works. And I am very empirical and very mercenary. I don't care how it ought to be. How it ought to be means nothing to me. How it is, that's what I care about. And that's a great question, by the way. I really appreciate that question. Next question. These are really great questions. I heard from CSs that they are the ones researchers should work with. How to see that? You mean like the CS researchers want to collaborate with the domain scientists and engineers and such? I think that's absolutely wonderful. I'm 100% on board. And that doesn't in any way reduce the impact that we can provide. The computer scientists are not doing the things that we're doing. And we're not doing the things that the computer scientists are doing. Nor should we try, nor should they try. Right? So absolutely, the computer scientists should be collaborating with the domain researchers. And absolutely, we should be providing the research, computing, and data capabilities that those teams need. That's not in conflict. On the contrary, it's complementary. More questions. I love questions. Yes.
Do you have any kind of example or tip or suggestion that the funding IT team could use to pursue faculty or even large departments or laboratories to be interested in collaborating on cyber infrastructure?
Yeah, absolutely. In fact, I've got whole talks on that. So if you send me an email, I'll send you my most recent, which is probably a couple of years ago, slide deck on exactly that topic.
Thanks.
And we're not doing it in this workshop, but we have done it in others of these workshops in previous years, particularly at the intermediate and advanced levels. I have a talk called, So You Want to Get a Cyber Infrastructure Grant.
So I'm new to the HPC team here at the School of Mines, learning, well, as fast as I can, but it's getting there. First project I was handed was to figure out how to bill by core hours. Sometime last year, and this is about the time I got on the team, this thing came up about grant funding language that says when a grant purchases something, it must be exclusive to the grant. So in our condo model that we had a year or so ago, they can no longer share those resources. There was also the argument made that the grant, if they didn't have the condo model and the school bought the computing equipment, they had to have equal free access, so they couldn't be charged for it. So a group of people decided, okay, well, we'll have a core hour, pay to play kind of model, which we have teams who have no funding, who were using the equipment when it was available. I'm just kind of wondering, what are other schools doing? How are you paying for the equipment?
So let me start with the disclaimer. I am not a post-award professional. So everything I say in response to your question is going to be to the best of my understanding based on discussions with both my research computing counterparts at other institutions, researchers, and research funding professionals. So that's the disclaimer. Now I'm going to start telling you stuff. The first thing is there are about as many different charging models associated with condominium supercomputing as there are institutions that do condominium supercomputing. Everything from, if you buy it, it's 100% yours and only you and the people you designate can use it and nobody else can ever be on it, which is effectively the model at my institution, to if you buy it, then you get a special queue where your turnaround time is guaranteed to be no worse than 12 hours or whatever, but everybody else gets to use it when you're not using it. Or you get a special queue that is next to run and everybody else gets to use it too. And all of these models are operating all the time. And I've never, ever heard of any institution getting in trouble for any of these models, ever. Now, is that an answer to the question, what is technically according to the written policy? I have no idea. But I've never, ever heard of any condominium model ever being a problem anywhere. And our business, the research computing business, is a very small town. We all meet in a phone booth, right? If something like that had happened, I feel confident everybody, not me, everybody would have heard about it. It hasn't happened, as far as I'm aware. If anybody's heard of such a thing happening, let me know. But I've never heard of any condominium model being rejected. Okay, so that's the first thing. The second thing is, to the best of my understanding, the rule for making capabilities available for federally funded research is federally funded research has to have a most favored nations status. That is, it can't be the case that something else gets better than what the federally funded research gets. It can be the case that something else gets worse. The feds don't care if you treat others worse. They only care that they're not getting screwed, right? To the best of my understanding. Again, disclaimer, disclaimer, disclaimer. The third thing is the fraction of institutions that do per core hour charges for research computing systems is pretty low. I had occasion to do a deep dive into our institution's aspirational peers. So this was 14 institutions who in federal fiscal year 2019 had research expenditure between about $310 and about $602 million for the institution as a whole, internal and external funding for that entire 12-month period. And so it was 14 institutions, and those 14 institutions, I believe 3 of them charged cycle charges. My experience or observation, I suppose, has been, because we haven't done it at my institution, my observation has been that most institutions that have started charging cycle charges have stopped charging cycle charges. And the reason that they have stopped, and this varies between very high research activity where they've got tons of money versus lower research activity. My institution's kind of in the middle, but except at the very high end, it's very difficult to make cycle charges work because one of 2 things happen. Either the faculty choose not to do computational research at all, or they choose to take their computing somewhere where they won't get charged cycle charges, which either means they're collaborating with someone at another institution and they do the work at that other institution, or they go to the national centers. And the national centers are poorly positioned to provide research computing capacity for everybody in the country. They are designed for want of a better way of thinking of it, projects that are huge, projects that are wee, and projects that are strange, that are weird, that need very quirky kinds of systems. And in fact, the latest solicitation from the NSF is for essentially split between capacity systems and quirky systems. They call it innovative, but let's call it what it is. Anyway, what ends up happening is you end up having less computational research at your institution. The price of that is that more and more opportunities require at least some portion of that funding to go to computational activities. And I don't mean in the sense that that's like written in there. It's that the expectation is that the computational component, the wet lab, the experimental component, and the theoretical component will all work together to advance that particular question or set of questions. So essentially, the risk you take is you will talk yourself out of the market. I did a thought experiment here about that some years ago. We calculated out what the per core hour cost recovery cost would be. And I looked at one of our biggest consumers of research computing at the time. And I calculated out how much funding we were facilitating as a center of his. And then I calculated what it would have cost him of that research funding to do his research computing with our center. And the answer was it would have consumed all of his money. And he was on tenure track at the time. He didn't have tenure yet. So he would have left or gone into the wet lab business rather than continue down the road because he wouldn't have had any grad students or postdocs and he wouldn't have been able to publish, right? He would have not gotten tenure. That's my concern with cycle charges. There are institutions that can make that a sustainable funding model. There are far more institutions that cannot. And I honestly don't recommend it. Okay, I don't know if that was exactly the question you wanted answered, but that's kind of where I am on those kinds of issues.
That's exactly what I was asking. Thank you. Helpful to hear that.
Okay, and I missed, okay, hang on. We would think that, but they often reinvent the wheel quickly, as cheap as possible. Okay, as an information security officer, this unsettles my stomach. I understand that. That makes sense to me. Reasons and efforts to woo researchers are also much used and needed by libraries. Yeah, absolutely. Right. Just because it's obvious to us that we would be immensely helpful, that doesn't make it obvious to them. Do you have statistical data showing the usage of, sorry, I'm trying to get that question and it was half on and half off here. Okay. Usage of CPU, GPU storage of user account per year. Yeah, they have to be gathered in somewhat different ways. CPU and GPU are pretty straightforward to get from the batch scheduler database. Storage is a bit more tricky. Now we do a regular warning email to people about our auto purging cycle. And so we do have much more storage usage data than we would otherwise have. And so we can identify big users of storage. We can identify users who do lots of IOPS based on having a large number of small files. Now, it is possible to do lots of IOPS on a large file. It's just not that common. So if we have a user that has a large number of small files, we assume they're doing heavy IOPS. If we have a user that has a small number of large files, we're assuming they're doing lots of sequential IO. And then we have a very small number of users who have both, although that's quite unusual. But there are some. And so we target a lot of storage. And I'm going to be talking about this tomorrow in my talk about designing an HPC cluster. We talk about this stuff, and we think a lot about those questions. But yes, we do gather that kind of data about our users, mostly to help us help them better, and some to brag to the higher ups about how swell we are. Okay, I am 19 minutes over my time with the questions. So let's wrap up. And we are meeting in an hour and 10 minutes. So you have a lovely lunchtime ahead of you. And then it's half past the next hour, not half past this hour, but half past the next hour will be the start of our next session. So 1:30 Central, 2:30 Eastern, I guess that's 12:30 Mountain and 11:30 Pacific. Is that right? I believe that's, let me double check, but I believe that's correct.
Yeah, I think so.
Yeah. Okay. So we'll see you all then. I'm going to keep this session open. I will stop the recording, but I'll keep the session open so you can come and go as you like. Leave yourself logged in, get some lunch, refresh your favorite beverage, and we'll see you in an hour and 10 minutes, half past the next hour. Thank you, everybody.